Hi everyone, this is Mr. Hall and this is a really quick video about mass changes and reactions. This is quite closely related to balancing equations as well as much other kind of lots of bits from quantitative chemistry. So if you understand balancing equations, hopefully you understand the idea of the conservation of mass, and that means that this idea around mass changes and reactions should hopefully not be too complicated to know. So the key objective really for today's video is to describe and explain the difference in mass between reactants and products. And there are two situations where there may be a mass change. There'll be a mass change if there is a gain in mass, and there will be a mass change if there is a loss in mass. And you should be able to describe and explain both of those situations. So we'll start off with a mass drop. So let's take the reaction between hydrochloric acid and calcium carbonate. Now, as you can see from the diagrams, on the left-hand side, which is over here, this is the start. So inside this beaker, which is on a balance, we've got some hydrochloric acid inside there, and we've got some calcium carbonate or marble chips, which are going to be added to it. Now, if I have both together on the balance like so, that would give me a mass reading, and let's just say for the sake of argument that that is 110 grams, okay, and that will read 110 there. Now, if I add those to the hydrochloric acid and let it react for several minutes, you'll find that the marble chips, the calcium carbonate, will be at the bottom for a while, and you're probably going to see some effervescence, some bubbling, and then over time the mass will drop. So it will go to something like 106. Now it will seem from that the mass has magically dropped, and that doesn't obey the law of the conservation of mass, but actually it does. But to understand why, you need to understand the chemical reaction involved in a bit more depth. So if we write out what the chemical equation is for this reaction, it's this. So we have calcium carbonate, that's your marble chip, which was on the balance over here at the start. You've also got hydrochloric acid, which is aqueous, and that's the liquid that's inside here at the start of the experiment. Then when they're added together, so at the bottom here, if you remember, you had some of these marble chips sort of hovering at the bottom. That will sort of discount for now because that's still reacted, and if you gave it more time it would eventually react and disappear. But what you effectively have is calcium chloride produced. Now that's aqueous, which means it's dissolved in solution, so that will be inside there. You've also got water, which is here, and that will be inside there obviously. And then you've got CO2, which is a gas, and that gas will escape out into the atmosphere, and that's the bubbling or the effervescence that you could see when you did the reaction. Now, the mass escaped from the reaction mixture as a gas, and it's that mass that's escaped which accounts for the change in mass on your balance. Now, if you remember, at the beginning on the balance it said 110, and at the end of the reaction it said 106. So that difference in mass is the mass of that carbon dioxide, and to work out how, you just have to take away one from the other. So it's 110, take away 106, and that gives me 4 grams. That is your mass of carbon dioxide gas. Now the important thing is that the law of conservation of mass is conserved, in as much as the mass of my reactants is still the mass of my product. So I still start with 110 grams of stuff and I end up with 110 grams of stuff. The only thing that you have to be careful of is taking account of where that's gone. Okay, and it's often because there's a gas which you can't measure on a scale. Now, if we look at this more on the atomic level to really understand what's going on, let's think of it like this. So I start off with calcium carbonate and hydrochloric acid. Calcium carbonate is on the left, and the hydrochloric acid is on the right. And if you remember, these are all inside a beaker, and they're slowly reacting with each other in solution. So this is my calcium carbonate, and at the beginning, that carbon dioxide will react like so, and it will form a gas, and that gas will go out into the atmosphere. Then my chloride ions from the hydrogen chloride will come over to the calcium to form calcium chloride, and then my oxygen will come over to form H2O. Now in truth this will be a Ca2 plus ion and a Cl minus ion, which are floating in solution, but we're not going to talk about that yet. But the key thing is that these are dissolved in solution and you can weigh them. Okay, so that and that, millions of them in solution, will account for your 106 grams. This gas which you're producing accounts for your 4 grams, and it's together that you get your 110 grams in total. All right, so although it seems like the mass has dropped, actually it hasn't. You just can't measure all of the mass. So that's one example of the mass drops. Now the other example you might get is if the mass seems to gain. Okay, now if the mass gains, again it might seem like it's not following the law of conservation of mass. Now the example we're using here is an iron wire which is being put inside a Bunsen flame, as you can see there. Okay, and over time you might find that the iron wire starts to get a bit darker, discolor, and at the start you might start with a mass of 1.5, but then over time it might drop to 1.7. And again, it seems, why is the mass changing in this particular way? Well, the reason why, again, can be found by looking at the chemical equation for this reaction. Now, if we look at this in a bit more depth, this is the reaction we've got. So we've got two lots of Fe, that's basically your iron wire. And then we've got O2 that it reacts with oxygen, and that is a gas in the atmosphere. So that is going to react with the iron wire. And that creates iron oxide, or FeO, and that is the outer layer on your wire, and that accounts for the increase in mass. Now the mass that you've got extra has been added to the reaction mixture from the atmosphere, it's the oxygen, and that gain in mass is the reaction oxygen that was added. So at the start, remember we started 1.5, that 1.5 was just the wire, okay, and then the 1.7 that we got at the end is the wire with that iron oxide. So if you wanted to work out the mass of the oxygen that was gained, again it's a case of simply deducting 1.5 from 1.7, and that will give you 0.2 grams. That 0.2 grams is your oxygen. Again, let's have a look at this at the atomic level. If we look at the atomic level, I've kind of zoomed in a little bit. So this yellow monstrosity, that's a zoom in of the flame which I had over here. And then this thing, what I've tried to do is show you what the wire would look like if I zoomed in. So I've given you two rows of iron atoms. Obviously, as a massive lattice structure, there'll probably be billions and billions and billions of atoms. I've just tried to simplify it by just showing you a few. So at the beginning you start with the iron and the oxygen, and then as they react, these oxygen atoms are going to bond onto the iron atoms to form iron oxide, and as you can see it will form this outer layer of iron oxide on the outside. So you started with oxygen at the beginning, that was your 0.2 grams, which you couldn't measure, and then the wire at the beginning was 1.5, but then as they start bonding together, that then turns into 1.7 grams because you've added the oxygen. So that's why you get this gain in mass. So I hope that's been helpful, and best of luck with your questions around determining changes in mass.